Hi everyone, in this session we're going to take a look at the memory subsystem. First off, we're going to take a look at what a memory subsystem consists of. Then we're going to look at the metal oxide semiconductor field effect transistor. That's a mouthful, the MOSFET. The MOSFET NOT gate circuit. Then how to construct DRAM circuits with MOSFETs. And then lastly, we'll look at one of the most common types of memory out there currently, the DDR5 DRAM. So memory subsystem. So the memory subsystem is an addressable sequence of storage locations. And it contains instructions and data for use by the processor. So modern systems contain over 1 billion 8-bit storage locations in memory. And each can be read from and written to by the processor. So from in the 1950s to the 1970s, computer memory was predominantly magnetic core based on polarity. So we had magnetic disks that were spinning. We had a read-write head that would access that memory. It's considered to be non-volatile, which means if you turn the power off, the bits would be maintained until we next turn the power on and access those locations on those spinning platters. Now, modern systems use what's called metal oxide semiconductor field effect transistors, or MOSFET. And it's called MOSFET-based DRAM circuits. And we'll take a little bit of a detailed look at how these work. And they use these for main system memory. So earlier on, we talked about the NPN transistor. So this is a type of bipolar junction transistor. So BJT is the acronym for it. And, NPN transistors rely on positive and on negative charge, which is why they're called bipolar, so positive and negative. Whereas MOSFET is what we would call a unipolar transistor. So it relies on only one charge carrier. And so, similar to NPN, MOSFET is a 3-terminal device using control input to turn the flow of current on and off. And terminals are called, we use a little bit different terminology. They use gate, drain, and source. So we're going to take a detailed look at a diagram in a second here, so just bear with me. So the gate terminal controls the flow of the current between the drain and the source, so similar to the NPN. So we either allow current through or we don't allow current through. So it's analogous to an on and an off state, a 0 and a 1. And we classify these using the terminology an enhancement mode or a depletion mode device. So we can configure this MOSFET in one of two different ways, enhancement or depletion. So let's take a little bit of a more detailed look at each of these. So basically, like what I'm saying here, we either block or allow current between the drain and the source. So we allow it through, right, or we block it. Those are the only two states we can have. And so here we have our two different MOSFET types. So enhancement mode blocks the current when the gate voltage is 0. Okay? So it allows current when the voltage is above the threshold, whatever that threshold may be. So 5 volts as an example. And we call it the N-channel type of MOSFET. The second type of MOSFET works in what we call depletion mode. So it blocks the current when the gate voltage is high. So you can see it's the inverse of enhancement mode. So it allows current when the voltage is at 0. So we call this the P-channel. So we have N-channel MOSFET in enhancement mode, and we have P-channel MOSFET in depletion mode. And we can put these together to create logic gates. So to distinguish between the schematic representations of the N-channel and the P-channel MOSFET, observe that the source terminal, so here's the source terminal, is connected to the center of 3 internal connections in both configurations, so here and here. But you can see that the direction arrow on the N-channel is the opposite of the direction arrow on the P-channel. So that's how we differentiate between the two. So N-channel, P-channel. So MOS transistors are often set up with an N-channel and a P-channel pair to perform logic functions. So you can probably guess where we're going with this, right? So if we use an N channel in combination with a P channel, what it essentially creates is a NOT gate. And we call this a complementary MOS or CMOS. So it's a complementary MOS or CMOS integrated circuit. And the advantage of this configuration is that it consumes very little power. So, modern computers, anytime we can conserve power on these devices, it's a very advantageous thing. So the only time that we consume power is when switching is taking place. So when we're converting from a 0 to a 1, or we're converting from a 1 to a 0, as an example. Or if we're replacing a space in memory with some new data, right, we have to configure those bits accordingly. And so here's our CMOS NOT gate circuit using our MOSFET P channel and N channel. Okay. So today, most all digital integrated circuits in use are based on this CMOS technology. So I'm going to get my drawing tool going here. And I'm going to go through this using both an input that is set to 0, so an input here that is set to 0, and then an input that is set to high, right, or on, which in this case, we're going to use the example of 5 volts. Okay. So when the input signal is low, so if the input signal is 0, the lower N channel MOSFET, the one here, the lower N channel MOSFET is switched off, and the upper P channel MOSFET, so I'm just going to put a cross through here, it's off, and the upper P channel MOSFET is switched on. So this connects the output to the positive side, so the positive side of the voltage source. So the P channel allows current when the voltage is 0, and so the output then in this case will be high, or so it will be 5 volts, right? So the P channel allows current when the voltage is at 0 here. So this connects the output to the positive side. The P channel allows the current, raising the output signal to near 5 volts, which is essentially 1. So input 0, output 1. Okay. Conversely, so let me erase this. Conversely, when the input is high, so we're going to start over here with an input of 5 volts, so essentially a 1, right? The MOSFET is switched off, the upper one, and the lower MOSFET is switched on, blocking current, so pulling the output down to near 0, right? Because that's what the N channel does. And so the output then becomes 0, or 0 volts, which of course is a 0. So when the input is 1, the output is 0. So the output signal then is always the inverse, as we can see, of the input signal. So the input is 0, I, right? The output is 1. Over output is 1. And if we input 1, then the output is 0, right? So that's a NOT gate. So this is basically a NOT truth table. Okay, so this particular CMOS circuit then represents the behavior of a NOT gate. Let's move on. So constructing DRAM circuits with MOSFETs. Sorry, my face is in the way there. So a single bit of dynamic random access memory, or DRAM, is composed of 2 parts: a MOSFET and a capacitor. Okay, so a capacitor is a 2-terminal passive circuit element capable of storing energy. Okay, so it can store energy for a period of time. So if it has a voltage running through it, then it will maintain that voltage for a period of time. So energy enters and leaves as electrical current. This is what a capacitor looks like in a diagram, an electrical diagram. And the term capacitance is the stored energy in a capacitor. And we use a unit of measurement called a farad. So the capacitor stores voltage, And with a capacitor, low voltage, of course, represents 0. High voltage for DDR5 DRAM, which we'll talk about in a second, that represents a 1. So if the capacitor has a level of farads that equals 1.1 volts, then that would be considered to be high voltage, so it would be a 1. So if we look at a DRAM bit cell, it's a readable, writable 1-bit storage location. So that's what's representative here. Okay, so it contains a MOSFET, which we can see here, and it contains a capacitor. So the 3 horizontal lines, which we see right here, these 3 horizontal lines indicate what we call a ground. And the word line here and the bit line here are used to connect into a grid. And usually we connect into, for example, an 8-bit grid. And I'll show you a diagram of that, I think, on the next slide. Yes, here we are. So these word lines and bit lines in a grid represent what we call a DRAM memory bank. And this is a picture of it here. I'm just going to slide myself up a little bit. There we go. So on the right, we have a DRAM memory bank. And this one happens to be 4 words of 4 bits each. So you can see we have, let me just get the drawing tool again here. We have 4 words. So here's our word line. And here's our bit line. So we have 4 words of 4 bits each. Okay, so here, for example, is 1 word on this row, 2nd word, so row 2, etc. Drawing tool. So typical DRAM banks are configured in 8-bit. So this diagram is just to represent it in a kind of smaller way that hopefully makes more sense. But typical DRAM banks will be in this 8-bit configuration and in parallel. So over 1 billion of these in a modern system. So a lot of these 8-bit banks will be configured within the guts of your computer. So the modern type of memory that's used is called double data rate RAM, or DDR. And it performs at 2 transfers per clock cycle. So it will allow reads and writes on the rising clock cycle and also on the falling clock cycle edge. And random access memory, or RAM, allows the processor to read or write any memory space in one operation because they're in parallel. So that makes this type of memory very, very efficient. And laptops, for example, the one that I'm presenting to you on right now, contain memory modules of 32 gig, which is a lot more than when I started using computers back about 30 years ago or more. So 32 gig modules. And as of 2021, the leading memory modules that are in use today are these DDR5 DRAM modules, and they're powered by 1.1 volts. And they can transfer at 4.8 billion data transfers per second, so incredibly quick, incredibly efficient, which is why they are so popular and in such wide use today. So that's all I wanted to talk about in this session. We talked a little bit about the memory subsystem. We looked at the metal oxide semiconductor field effect transistor, or MOSFET. We looked at a MOSFET NOT gate circuit, which was a combination of a P-channel MOSFET and an N-channel MOSFET. We looked at constructing DRAM circuits with MOSFETs, so how we can configure them using word line and bit line into 8-bit banks that can be read and written to in parallel, which makes them very quick and efficient to access for reads and writes. And they could be done on a rising clock cycle with DDR5 DRAM and also on a falling clock cycle. So DDR5 DRAM is the most popular type of memory that's in usage today. All right, thank you for listening.